Zeal Education Society, redefining excellence.
Good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. In this video lecture, we are going to learn various torques of the synchronous motor. Now, what is the first one is, just a minute. What is the starting torque? It is the torque developed by the synchronous motor when full voltage is applied to its armature winding. The starting torque, it may be 10% in case of centrifugal pump and may be as high as 200 to 250% of full load torque for reciprocating pumps. Now the second one is running torque. Its name implies that it is the torque developed by the motor under running condition. It is generally obtained from the horsepower rating and the speed of the machine. The motor must run at a running torque less than starting torque and maximum torque to avoid the stalling. The next one is the pull-in torque. Its name implies that the amount of torque required to pull the motor into synchronism during starting. Now you are well aware that synchronous motor is inherently not self-starting. However, by using the damper winding, which are nothing but the heavy aluminum or copper bars placed in the pole shoes of the rotor and which are short-circuited on both sides by end rings, thus the synchronous motor rotor behaves like a squirrel cage rotor. So when three-phase supply is fed to its armature winding, synchronous motor runs like a three-phase induction motor near to synchronous speed, very close to synchronous speed, and when the DC excitation is fed to the rotor winding or a field winding, the motor pulls into synchronism. So the amount of torque required to pull the motor into synchronism and to run at a synchronous speed is known as pull-in torque. Then the next one is pull-out torque. It is the maximum torque that the motor can develop without losing the synchronism, or in other words, it is the maximum value of the torque at which motor falls out of synchronism, pull out of the synchronism. We know very well that when the load on the motor is increased step by step, gradually go on increasing the load, rotor retards back and the angle is generated between stator polar axis and rotor polar axis of opposite poles. Now this angle delta goes on increasing. A stage will come or angle delta goes on increasing. Still there is a magnetic locking between stator poles and rotor poles and motor continue run at a synchronous speed. However, if you go on increasing the load, a stage will come at which that the angle, when the angle delta becomes 90 degree, there would be no magnetic locking between stator poles and rotor poles and motor falls out of synchronism. So this thing I have shown by the animations, you can observe here carefully. See the first case, here it is. For simplicity, I have shown that in actual practice, I have stated so many times, the stator of synchronous motor, stator of induction motor and stator of synchronous generator. The construction is same. There is no physical appearance of the stator poles. In fact, the poles are decided as per the requirement of the speed and accordingly the armature winding is wound for that number of poles. Now for simplicity, for better understanding, I have shown here the stator pole is also projecting away and here we have considered only the two-pole machines. Rotor is also two-pole, stator is also two-pole machine. Now when the three-phase supply is fed to the stator armature winding, it produces the rotating magnetic field, say shown by the magenta color arrow. It is rotating in a clockwise direction, and say the rotor is also rotating in a clockwise direction shown by the arrow. Okay. Then when the motor is loaded, mechanical load is put on the motor, rotor falls back. Rotor falls back by an angle say delta equal to 30 degree. We have considered nominal as a 30 degree. It may be any degree, no matter. So what is the angle between stator polar axis and rotor polar axis? That angle is delta and it is also known as load angle or a torque angle or angle of retardation or a power angle. But remember that though the rotor falls back and the angle is generated, still there is a magnetic locking between stator poles and rotor poles, and motor continue to rotate in a synchronous speed. Now say these are the certain nomenclature. The magenta color arrow shows the direction of rotating magnetic field which rotates at a synchronous speed. Then this pista color arrow shows the direction of rotation. Then the magenta color dotted line shows the rotor polar axis, and the black one shows the stator polar axis. Now if the load on the motor is further increased, rotor further falls back, retards back, an angle between the stator polar axis, that is stator polar axis, and rotor polar axis is further increased, say delta is equal to 45 degree. Still magnetic locking between stator pole and rotor poles is there, and motor continue to rotate at a synchronous speed. Now if you further load the motor, see what happens. The angle between stator polar axis and rotor polar axis becomes 90 degree electrical. Remember this word electrical. 90 degree electrical. There would be no magnetic locking between stator poles and rotor poles, and motor falls out of synchronism. So at this condition, what is the torque developed? That torque is known as maximum torque, and that is also known as pull-out torque. At this torque, motor pulls out of synchronism, and that's why it is also known as pull-out torque. Hope you understood it. We will proceed further. The synchronous motor with different excitations. Okay. Remember that here it is shown the delta. Now when, see the figure 1, in figure 1, the back EMF, this is the supply voltage V or voltage per phase, and this is the EMF generated in the armature of the winding, that is, it acts in opposite direction to that of the supply voltage, and hence it is known as back EMF. So when the magnitude of the back EMF is equal to the per phase voltage, we can say it is a normal excitation, or in other words, it is a 100% excitation. And in that case, we can say it is a motor is running at a lagging power factor. In this case, motor is running at a lagging power factor, the armature current is less, and the phase angle phi is also less. If you observe the second figure, in a second figure, the excitation is less than 100%, we can call it as a under excitation, and motor runs at a lagging power factor. And in that case, the generated EMF, EB is less than phi. EB is less than phi. So in other words, at 100% excitation and at a less than 100% excitation, or in other words, normal excitation and under excitation, motor works at a lagging power factor. Show here. See here, IA lags phi by an angle phi. But here in this case, it is a large angle. Now let us consider the third case. In a third case, the excitation is more than 100%, and we can say it is a overexcited case, and in that case, motor works in a leading power factor. Motor draws a current which leads the voltage by an angle phi. In that case, the back EMF generated, EB is greater than phi. EB is greater than phi. Okay. Now in a last case, EB is greater than phi. EB is greater than phi, but so at a certain excitation for which power factor of the induction motor becomes, synchronous motor becomes unity, and it draws the minimum armature current. It draws the minimum armature current. However, EB is greater than phi. So EB is greater than phi for a leading power factor as well for a unity power factor. Okay, and for a unity power factor, current drawn by the armature is minimum, whereas current drawn by the armature during lagging power factor and leading power factor is large. Okay. Now further we will study the phasor diagrams under various power factors. See, for a unity power factor, say OA is the voltage per phase, it is taken as a reference. Then as it is a unity power factor, angle between voltage and current is 0, and therefore current and voltage are on the same line, phi equal to 0. Now draw the resultant ER by making an angle theta with respect to I, where theta is constant. Theta is constant and depends on the winding parameter, theta equal to tan inverse XS upon RA. Okay, so sometimes for a large machine RA is 0, and in that case the theta may be 90 degree, otherwise theta is always less than 90 degree. Remember that theta is also known as internal angle, and which is the angle between armature current and resultant EMF ER. Okay, this ER is nothing but IA into ZS. Join AB, that indicate the EB, back EMF. The angle between VPH and back EMF is delta. Angle between VPH and EB is known as delta. So this is the phasor diagram for at a unity power factor. Okay. So at a unity power factor, we have already learned that EB is slightly greater than VPH. Here also you can observe EB is slightly greater than VPH. In that case, or in case RA is 0, theta is 90 degree, else theta is always less than 90 degree. And it is given by theta equal to tan inverse XS upon RA. This theta is also known as internal angle, and it is the angle between the armature current and resultant EMF ER. And the angle delta, which is known as load angle or a torque angle or a power angle, it is the angle between VPH and EB. So how to find this angle delta or the load angle? It can be obtained by using the sine rule applied for this triangle. The triangle is acute angle triangle. Okay, so here it is ER, that is OB. OB is ER divided by sine of the opposite angle. Sine of opposite angle is delta. So ER upon sine delta equal to, this is EB, back EMF, and its opposite angle is theta. So EB upon sine theta. In this way we can calculate the load angle delta. Okay, now how to find this EB, back EMF? How to find the back EMF? This back EMF, we know the VPH and we can calculate ER equal to I into ZS. Because ZS, RA and XS is known to you, you can find out ZS, and we know the armature current. A product of armature current and ZS gives you resultant EMF ER. So we know the two sides of the triangle, ER and VPH, we can find out third side, and that can be given as EB square equal to VPH square plus ER square minus 2 times VPH into ER into cosine of angle between them. So what is the cosine of angle between VPH and ER? In this case it is theta, so cos theta. Remember that EB is slightly greater than VPH in this case. Okay, so in this way we have finished the phasor diagram for a unity power factor. Let us consider the phasor diagram for a lagging power factor. In this case the EB is less than VPH. EB, you can observe the EB which is less than the VPH. Now VPH is drawn as a reference, OA represents VPH. Draw the current IA by making an angle phi, lagging to the VPH by an angle phi. Okay, so in this way we have drawn VPH and IA. Now draw the ER, resultant EMF, that is known to you, that is equal to ER equal to IA ZS. And the angle theta, which is fixed, that can be internal angle. So draw the ER by making an angle theta with respect to I. Okay, so in this way we have drawn the OA, VPH, OB, ER by making an angle theta with respect to I. Then join AB, AB represent the back EMF or induced EMF. Okay, then angle between VPH and IA is angle delta, that is known as load angle. But in this case, what is the angle between VPH and ER? That is shown by this one. That is in this case theta minus phi. In this case theta minus phi. Okay, so in this way, how to calculate the load angle delta? That can be also obtained by using the sine rule. The same fact we have to use here. The ER, which is known to you, ER divided by sine of opposite angle, that is sine delta, equal to EB divided by sine of opposite angle. EB divided by what is the sine of opposite angle? That is theta minus phi. So that is nothing but the angle between VPH and ER. Okay, in this way we can calculate the angle delta. And this angle theta, this theta already I have stated, which is fixed angle, and that is the angle between the ER and IA. Okay, and now how to calculate the EB? Okay, so by using this acute angle triangle, the VPH and ER is known to you, we can find out the third side of the triangle. So VPH square, EB square equal to VPH square plus ER square minus 2 times ER into VPH into cosine of angle between ER and VPH, that is theta minus phi in this case. Okay, in this way the phasor diagram for the lagging power factor is finished. Now we can see the phasor diagram for the leading power factor. Now this is the wide angle triangle. This triangle has a wide angle triangle. The angle A, angle between OA and OB is wide angle triangle, greater than 90 degree. Okay. Draw the OA as a phase voltage as a reference, then draw the current OI, leading the voltage by an angle phi. Then draw the ER by making an angle theta with respect to I. ER is known to you, theta is also known to you. Theta angle is fixed for a certain winding parameters, that is based on winding parameter. And in this case, for a leading power factor, EB is greater than VPH. You can observe here also. Then join AB. Join AB. AB represent EB. Okay, back EMF. Now for this also, how to find the angle delta, that is the load angle by using the sine rule. Now once again the sine rule is same, apply ER divided by sine of delta equal to EB divided by sine of theta plus phi, because the angle between VPH and ER is theta plus phi, and in this way we can find out the angle delta. Now how to find the EB, because the two sides of the triangles are known to you, VPH given rating of the synchronous machine, then ER is nothing but IA ZS. IA is the full load armature current and ZS is the synchronous impedance of the machine, which is known to you. So these two sides are known to you, we can find out third side. So VPH square plus ER square minus 2 times VPH into ER into cosine of angle between VPH and ER. In this way we can obtain this angle. So in this way we have studied the phasor diagrams for a unity power factor, lagging power factor and unity power factor. We will stop here. Thank you very much.